All right, and with that, I'll get started. So our first speaker today is Maria Vincent. Maria is a third-year astronomy PhD candidate at the Institute for Astronomy, University of Hawaii at Manoa. Her research concentrates on adaptive optics and high-contrast imaging science and instrumentation with ground-based telescopes. On the science side, she has utilized the Subaru Coronagraphic Extreme Adaptive Optics Suite to observe and study morphological features of protoplanetary disks in near-infrared wavelengths to understand disk structure and processes governing planet formation. She is currently based at the WM Keck Observatory and is working on the high-order advanced Keck adaptive optics, or HAKA project, which is implementing a new 3000 actuator deformable mirror, DM, to the Keck 2 adaptive optics bench, with a focus on preparing the optics lab in and testing the new DM. Beyond research, she's actively involved in public outreach and regularly gives talks in schools worldwide on different astronomy topics. She is from Dubai, United Arab Emirates, and graduated magna cum laude with the highest departmental honors in geophysics and astrophysics from the University of California, Los Angeles. Maria's talk today is entitled Entering a New Era of Adaptive Optics with More Powerful Deformable Mirrors. So Maria, whenever you want to go ahead and get started, take it away.
All right, thank you so much, Tiffany, for the really lovely introduction. Hi, I'm Maria, and as you can see on my opening slide, I'll be talking about adaptive optics upgrades involving an upgrade to a better deformable mirror system on two telescopes, as you can see pictured here, Subaru and Keck. Before I begin, I'd like to recognize and acknowledge the very significant cultural role and reverence that the Summit of Mauna Kea has always had within the indigenous Hawaiian community. And I consider myself very lucky to have this opportunity to be able to observe from and work on this mountain. I would also like to thank the respective instrument teams at Subaru Telescope and Keck Observatory for giving me this opportunity to work with them on these projects that take us to the next generation of adaptive optics and prepare us for the upcoming era of extremely large telescopes. I am very, very grateful to my thesis advisors, Mike Bottom and Jonathan Williams, for their support and for connecting me to these institutions and the various projects that I'm a part of today. So before I jump into the details of my project, let's start from the very basics, which might be a little too basic for some of you. This plot right here gives a brief overview of the demographics of the planets that we have discovered so far. And this talk is about technologies. Whoops, sorry about that. This talk is about technologies that are motivated by the yellow spots on this plot, which represent the planets that have been discovered through direct imaging or high contrast imaging. And the goal of updating technologies is to have more planets visible to us, not just through radial velocity or transit techniques, but also we're in a position that we're able to take pictures of those planets and this empty part of the parameter space. So many of you may be familiar with this. High contrast imaging is a technique that helps us directly detect faint sources such as planets and circumstellar disks, which are very close to bright stars. Here you see the HR 8799 planetary system with its 4 planets, which are visible thanks to this technique. And this technique is largely motivated by a confluence of instrumentation and post-processing methods, including adaptive optics, which is what I'll be talking about soon, chronography, which is a method to suppress the central starlight, and differential imaging, which is a post-processing technique that deserves its own talk, but it basically helps us reduce speckles and make the planets more visible. The plot here shows the contrast, which is a ratio of the planet brightness to star brightness versus apparent angular separation for planets that have been discovered. And it's also, I think, a very neat way to demonstrate the limits of current and future instruments. The filled orange circles indicate the direct imaging detections of various young self-luminous planets by near-infrared instruments on ground-based telescopes. The orange curves show what our current instruments are capable of. The goal is to move closer to this orange-brown dashed line, which represents what future extremely large telescopes can be capable of, as well as what the next generation of space telescopes can detect, which is indicated by this black line right here and the pink line right here. Ideally, we want to be able to detect, if we were aliens on another planet launching these telescopes, we should be able to detect Earth, which is at a contrast of 10 raised to minus 10. And this is the ideal goal that we're all trying to achieve with every little instrument upgrade within adaptive optics. An important part of being able to see these exoplanets, at least I believe perhaps the most important part, is to develop starlight suppression techniques, which is what Zara's talk is going to be about. In my talk, I'll be focusing mostly on the first, or I guess the earlier component of direct imaging, adaptive optics. This diagram right here is a neat way to explore the basics of the AO workflow. You have an incoming wavefront that is distorted due to atmospheric turbulence, and it hits and bounces off a deformable mirror, or DM for short. And then this light is split into two parts by a beam splitter. One part goes to the science detector, the other part goes to the wavefront sensor. The wavefront sensor measures the distortions in the wavefront, and accordingly, the deformable mirror can change its shape to correct for these distortions. And in the end, once the deformable mirror has achieved the optimal shape, the corrected wavefront enters the detector, and you get your perfect, nice PSF, or point spread function. The part that I'm concerned with for both my projects is a deformable mirror right here, and we will look at this in a little bit more detail shortly. These techniques and their upgrades are motivated by a very simple question. What can we see, and what more can we see? What can we learn, and what more can we learn? And that's precisely what motivates the two AO upgrades, which I'll be covering in the rest of my talk. One of them is the high order Keck adaptive optics upgrade, or HACA for short. The goal is to improve corrections of the atmospheric fitting error in order to optimize the Keck AO system's performance for high contrast science. And we hope to achieve this by upgrading the deformable mirror, Shack carbon wavefront sensor, and real-time control system on the Keck 2 AO bench in order to create a new high-order deformable mirror system. The other upgrade I'm talking about today is the Adaptive Optics 3K, or AO3K for short, at Subaru. The goal here is to reach deeper contrast for high contrast images, to be able to see fainter targets for imaging and spectroscopy, and detect redder targets through a phase-wise upgrade of the AO system. Phase 1, which has been successfully completed, was to install a new near-infrared pyramid wavefront sensor. Then there's the upgrade to a high-order DM, upgrade to a nonlinear curvature visible wavefront sensor, and an upgrade of the real-time control system. A major science objective for both these instrument upgrades is something that we're all interested in: exoplanets. The high-order DM helps increase the intensity of the observed PSF and allows direct imaging and spectroscopy characterization of exoplanets that are too close to their host stars for JWST to see them, or too cold to be accessible to today's ground-based telescopes. This plot right here compares the contrast limit of JWST, which is the dotted line, to that of the current Keck AO system, which is this thin solid line, to that of the HACA upgraded AO system, which is thick solid line. As you can see, the contrast achieved with the HACA upgrade is much deeper, meaning we can see fainter planets, and based on the location of the line, we can see things that are much closer in, or closer to their host star. The HACA upgrade will also nearly double the number of detectable exoplanets from Gaia's next data release, which will be a part of Gaia's extended mission around the time when HACA will be completed. So we'll be going from, so currently with a new upcoming imager called Scales, we'll be able to detect 12 Gaia's, we'll be able to detect planets around 12 Gaia stars, and HACA upgrade will take that number to about 22. The circles on this plot show the Gaia planets, which have mass of less than 13 Jupiter masses, and brown dwarf companions that will be detectable with the current AO system, versus the ones in the stars, which will be detected with the upgraded AO system. HACA will also enable high contrast, high resolution mid-infrared spectroscopy, which will allow line-by-line identification of molecules. This will break the degeneracies that plague atmospheric characterization with imaging alone, resulting in detailed measurements of molecular abundances, including previously unobserved species. It will also help us better understand metallicities and surface gravities for significantly colder planets that we can currently directly image. Besides exoplanets, HACA can also enhance the imaging of protoplanets in their nascent disks, which makes it possible for us to observe active mass accretion, like in the case of PDS-70b, which is perhaps the most famous protoplanet that has been discovered in its disk yet. For confirmed detections of embedded protoplanets, we will need to separate the emissions from the disk's forward scattered light, and this would require high spatial resolution and a spectral resolution that covers a wide range of wavelengths where the protoplanet would be bright, which is usually near to mid-infrared. The high order deformer can separate this protoplanet light, which is marked in this red solid line right here. Or sorry, the purple solid line right here. And this would be achievable at a space scale of about 5 to 10 AU, and will be sensitive to accretion luminosity, is a factor of about 5 lower than current Keck AO system. This will help us also constrain spectral signatures at near infrared wavelength, which is basically what the bottom panel here shows, in order to confirm the presence of protoplanets and characterize their accretion rates. For protoplanetary disks, HACA will also enable high-res mapping of various ice and organic features in these disks. Another key science objective is to improve solar system science by achieving short wavelength AO corrections, because right now we get good corrections within the near infrared, but doing adaptive optics is a little bit harder in shorter wavelengths because of how turbulence scales with wavelength. So the goal is to be able to achieve this at least in Z band to start. And this is useful if you have to study the atmospheres of our solar system's ice giants. Now, right here is a very popular visible light image of Neptune from the Voyager spacecraft. With the higher resolution of the new DM, we can go from 76 milliarc seconds, so a fuzzy cloud-like feature, to 32 milliarc seconds, which is a less fuzzy, more definite cloud-like feature. And this is also useful for geological mapping for surfaces of Galilean moons with smaller wavefront errors. In this picture right here, we have the surface of Europa. The red circles compare the current Keck and the upcoming HACA resolutions. So the tighter resolution means that the new DM can resolve the outlines of the tectonic chaos terrains of Europa and isolate mid-sized impact craters. The blue and green ellipses outline the plausible plume sources, and with the better resolution, we can now directly target these plume sources in order to obtain more definite compositional constraints. The Subaru DM also hopes to achieve similar goals. One of their primary goals was to enhance imaging and spectroscopy of stars orbiting the black hole at the galactic center. Greater the number of actuators with a deformed mirror, greater is the correction that we achieve, and we also improve what we call the Stroll ratio, which I'll explain in a little bit. And this helps better constrain the observations of the stars of the galactic center and spatially resolve spectral observations. A combination of the near-infrared pyramid wavefront sensor and the high-order DM will also get us to redder, which are K2M stars, and stars with dust extinctions. And this is very, very important because these are the prime targets for imaging habitable planets for extremely large telescopes. Now, as I mentioned earlier, the goal of a deformed mirror is to apply the right shape in order to correct the distortion in the incoming wavefront. This is accomplished by changing the shape of the deformed mirror using these piston-like things you see in the figure called actuators. Actuators can move up and down a few microns depending on the voltage we apply in order to get the appropriate shape of the mirror to match the wavefront. And so we apply equal and opposite shape of the estimated wavefront in order to correct for any turbulence that's there. Now, why do we need a new deformed mirror on these super telescopes? To give some perspective for Keck, the current Keck-2 DM is kind of old. I was only 5 months old when it saw first light in February 1999. It has about 350 actuators and achieves a Stroll of 60% at 2 microns. Stroll is the ratio of the peak intensity of the observed point spread function to the peak intensity of the theoretical diffraction limited point spread function. It is a metric that we use to characterize the performance of adaptive optics instruments and describe how sharp or how crispy of an image that we can get. We are pretty much at the limit of what Keck adaptive optics can currently achieve. The scientific productivity of the telescopes rely on technological upgrades that keep the system and its associated science instruments at a cutting edge of AO performance. The new DM is going to be much more powerful. It has about 8 times the number of actuators, which is about 3,000. And this means that we can achieve a much higher order of correction. The Stroll ratio will be about 70% at 2 microns. And the high order DM will also reduce the fitting error by a factor of 2.4. The fitting error is the residual error due to the inability of the wavefront compensator to exactly correct the wavefront that is distorted by the atmosphere, and this can be controlled by the number of actuators. A 10% improvement in the Stroll ratio may seem really small, but it's but it is important because of how it relates to the fitting error as shown in this rough equation right here. It's an exponential relation, so even a 10% increase in strobe means we are reducing the fitting error by a fairly large factor. In this case, about 2.5. This is a diagram of the cross-section of the new deformable mirror system. The surface is a continuous membrane that is controlled by magnetic coil actuators, which are very similar to the ones that are used in loudspeakers. This is connected to a printed circuit board that is connected to the cabling, and the cabling goes to a rack of the DM electronics that basically drives the different actuators. A quick comparison between the old and new deformable mirrors at Subaru. The old one is about 18 years old, and it's our first light with the laser guide star in October 2006. It is a 188 actuator bimorph DM and achieves a stroll of up to 40% in H-band. With the near-infrared pyramid wavefront sensor, it will be able to achieve about 65%. The new deformable mirror, however, has way more actuators, about 3,200 of them, and up to 80%, 85% of stroll was seen with the near-infrared pyramid wavefront sensor in H-band. And I will show pictures of that towards the end of the presentation. Now that you have a basic idea of why these upgrades are motivated, what exactly we are grading, an important part, which is pretty much a big chunk of my thesis, is to test these deformable mirrors to make sure that they perform, that they achieve the level of correction that we need, they achieve the optimal performance that we want them to before they're taken up to the summit. And there is a procedure that we follow, and the very first step is to actually build an environment to test this deformed mirror. This right here is an optical diagram of what a basic optical test bench would look like. It consists of a light source, which is usually some sort of a fiber optic cable or a laser source and this light source hits a combination of off-axis parabolic mirrors, which are used to collimate the beam towards the DM. Right here is a flat mirror, which is currently used as a placeholder at CAC before the new deformed mirror arrives. And the OAPs can also be used to converge the light beam to an imager, as shown over here. This diagram, as I'm pretty sure, is very confusing for a lot of people, including me. So here is sort of the real life version of it. Right here are the off-axis parabolic mirrors, which are facing the flat. This is the light source. So you have light coming in from the source, hitting the first OAP, then going to the flat, then hitting the second OAP before it goes to the imager over here. There are some extra components over here that wasn't there in the previous diagram. One of them is a PSM, or a point spread or a point source microscope, which is a very helpful tool to align the optics. How it works, why it works the way it does, deserves a talk of its own. So if you have any questions, you can let me know after the talk. An interferometer is used to interferometer is basically a very nice and also very expensive optical tool to look at your mirror and take measurements of it, to measure the surface, how curved it is, how bumpy it is. And this is very useful when we start characterizing the deformed mirror, as I'll show in the plots in the upcoming slides. These two little spheres on a post on a plate called the alignment plate are used to help align the optical axis along as prescribed by the optical diagram. Because in order to have the light hit all the mirrors completely to get maximum possible beam size into our imager, we need to make sure that we're not losing light. It is going as it's prescribed, as it can be handled by the parabolic mirrors we have here. So these are mechanical references. You can think of it like the object and the image of a simple optical diagram that help align the optical axis. These are some pictures of what the test bench looks like. In reality, it is a little bit messy with a lot of papers for diagrams, a lot of additional tools, like this tool I'm handling here called Romer Arm, which it basically measures where things are on an optical table and compares it to a mechanical or a CAD model. And it's a very easier and more efficient way of positioning things rather than positioning things by eye. This is a different type of an alignment instrument called an alignment scope, which also helps with alignment. And here is sort of the beam that you can see with the alignment scope. So once all of this is set up, which is a clumsy, clunky, but a very rewarding process, you have to characterize a deformable mirror, which consists of two steps. One is functional testing, where we make sure that the DM can turn on and off, it works properly, the actuators can be poked, our system talks to the DM and the DM responds, etc. The other testing is called a performance testing, where we test the performance of the deformable mirror. We measure different aspects of it, and we compare it to what the manufacturer has prescribed. And through this, we get a lot of information about the deformable mirror, and we can construct an actuator model in the software pipeline of the deformable mirror, which becomes important once the wavefront sensor starts talking to the deformable mirror. And these are some pictures from when we unpacked and set up the unpacked the deformable mirror and set it up at the lab at Subaru. As you can see, a lot of it is about just getting your electronics right. The one big, I wouldn't really say a con, but something we have to be careful with really large DMs is making sure that we don't step on the many cables and the cables go in the right slots. Otherwise, it can really mess up the way the actuators work. So right here is an example of a measurement done with the Zygo interferometer. And this one right here is a gain map. A gain map basically demonstrates the stroke of individual actuators. How much do each of the actuators move when a certain voltage is applied? So for this test, we sequentially apply the same voltage to all the actuators, and then we produce a map measuring the amplitude of each of these actuators. In an ideal scenario, this map would be the same color throughout, but this is in the real world, actuators don't exactly move to the same height for a given voltage. So we would like a very, very small difference between the most moved versus the least moved actuators. And in this case, the difference is pretty fine, except for what we call a lazy zone, lazy zone over here, where a lot of the actuators some of the actuators didn't move as much as the rest of its neighbors, which in this case works fine because there's a pupil mask in front of the Subaru deformable mirror. Oh yeah, I should mention, the test results I'm showing right now would be for the Subaru mirror because the Keck mirror hasn't arrived yet. So in this case, a gain map is really useful because it helps us understand how much each actuator can move and diagnose any preliminary issues a certain actuator might be having. The next thing we test is to make sure that is to check the residual positional error from previous actuator positions and the repeatability of the stroke. Can an actuator be pushed from one extreme end to the other extreme end and come back to its starting position? So we basically pushed some select actuators from a negative to a positive stroke. So we pulled an actuator to a certain level and we pushed it out to another level. And then we repeated this test multiple times as a feedback loop to see if it's repeatable, if the actuator loses information in between, if it kind of like an elastic band, really. This is a hysteresis test. Can it come back to the same shape as before? And we see that it really does, except for this one wayward point, which basically when we started the DM from a cold start, meaning the DM was turned off before we started these measurements. But for most part, the measurements are repeatable. The actuators do start and finish at the same point, which is a good sign because the deformable mirror is going to be running at really high speeds for adaptive optics at around 1,000 to 2,000 hertz. So we don't want an actuator to be lagging behind or be outperforming the ones, somehow outperforming its neighboring ones. And another test, a very important test that we do is to see how stable these actuators are. Creep is basically a slow and time-delayed deformation of any material as a response to mechanical stress applied. The mechanical stress right here is the voltage we apply to different actuators. We see whether the actuator continues to expand a lot or contract a lot, even if after a voltage change is complete. So it's a test of stability of these actuators under prolonged stress. And we see that the actuators continue expanding after a certain time where we applied the voltage, where the points where we apply the voltage are the sharp drops and rises in the plot. But for most part, they're very stable, except for the parts where they aren't, where you can see these little wiggles, but those were basically due to errors in the Zygo measurement. But for most part, the actuators are stable, and this is good for us. I presume a lot of you may not have seen how a deformable mirror works in real life. So here's a little video I took of the mirror at the Subaru lab. As you can see at the reflecting surface, it moves fairly fast, although in real life, it moves much faster than this. This one was at a few hundred hertz. In reality, it moves about 10 to 20 times faster than this. Now, we also, and the last stage of the lab test is basically we have to ensure that we can close the AO loop in the lab, that is integrate the deformable mirror with a wavefront sensor, which is the entire relay optics that is covered in this white box of the lab photo. So we have to make sure that the wavefront sensor can measure the turbulence and talk to the deformable mirror, and the deformable mirror can get those corrections done. And I'll show you a video of what the deformable mirror looks like when these corrections happen a little bit later in the presentation. So once everything works well in the lab, we are ready for Summit installation. And as I mentioned earlier, since the deformable mirror that's actually arrived is the one at Subaru, the Summit installation is also going to feature photos and plots from the Subaru DM. So this is what the setup looks like at the Subaru AO bench. On the right are all the many cables that go here and there from the drive electronics to the deformable mirror, and something that we have to be very, very careful with. And on the left is inside the AO bench, which is basically a big box covered in a panel. And when you open the panel, this is what you see. On the bottom, you can see the deformable mirror right here, and this mirror corrects for tip and tilt. And this is a close-up of the deformable mirror mounted on a plate. And this is sort of how it's being installed in an adaptive optics bench. So the first thing that we did was a functional testing of the deformable mirror to see if it can turn on, if it talks to the other optics in the AO bench, and if it can adapt the shapes that we applied to it. On the top row are pupil plane images, and on the bottom row are near-infrared wavefront sensor images of this deformable mirror. From left to right, we have the rest shape of the deformable mirror, that is right when the deformable mirror is turned on and nothing has been done. Then we have the best flat, which is basically all the actuators at the same level, which is a good place to start when you start applying corrections. And this is the flat plus a bullseye applied to the deformable mirror so that we can sort of center on what we can identify the central coordinate on our image. And this is the logo of the project applied on the deformable mirror, because why not? And this is what it looks like. It looks like to the pyramid wavefront sensor, which are 4 pupil images. And that's how a pyramid wavefront sensor works, which unfortunately I don't have time to cover in this talk. So this is what I meant by what the looks like when we close the AO loop, when the turbulence is corrected. If you can see the top right, you can see a lot of turbulence, a lot of waves going over these 4 circles, which is 4 pupil images of the deformable mirror. And once the AO loop is closed, which is about now, you can see most of these changes have been smoothed out. Turbulence is fast. These cells move pretty rapidly, so you still see some motion, but it is more uniform than before. And this is to show comparison between before and after having the deformable mirror. Right here is an image of a 8.3 magnitude star, which we use as a reference star for a lot of adaptive optics corrections, which right before having the deformable mirror, we achieved a stroll of about 65% in H band. Now, after having the new deformable mirror, we observed a different star at a similar magnitude. Sorry about that. And that's this one right here. And with this, we were able to achieve almost a 20% increase in stroll. The conditions were fairly the same, although this one the bottom star was observed at slightly better conditions. But this is to show how much of an improvement we can expect in observations with just changing out the deformable mirror. And to conclude, just to wrap all of this up, the major goal of these upgrades is pretty much better exoplanet science in addition to galactic center observations and solar system science. We will be able to access a less explored regime of planets in direct imaging, which are exoplanets that have lower contrast than those detectable by JWST. We can improve atmospheric characterization of exoplanets with more resolved spectral lines and identify more tenuous molecular species. The red box in this plot is basically the current direct imaging capabilities, what we can see right now. And we are trying to move towards the blue box where we have redder and fainter targets, which can be imaged and have their spectra observed with the next generation of extremely large telescopes. And where are we with the upgrades right now? In the case of Subaru, the new DM is being tested on Sky. It's been installed, and engineering group nights so far have reported much higher stroll. And at Keck, the lab setup is in progress, and I will hopefully have nicer and newer images at a future talk once the deformable mirror arrives in November. And to give a big picture view of this whole thing, why are these even important in the first place? one of the major reasons why we are focusing on these upgrades right now is because they are a technology demonstration for improvements in wavefront control and particularly short wavelength adaptive optics, which will be really vital for future extremely large telescopes. These adaptive optics upgrades on 8 and 10 meter class telescopes are there so that the extremely large telescopes can run smoothly in the future. Thank you so much for listening. I might have hit the 30-minute time already. Yes, I almost are. I'm there. So hopefully you all learned a lot, and yeah, looking forward to some discussions after this. Thank you.
Thanks a lot, Maria. Unfortunately, we actually don't have time for questions. So Maria, if you want to put your email in the chat, and so if folks want to get in touch if they have questions about your talk, they can do that.
Sounds
All
good.
right. Thanks so much, Maria. We should move on.